Good morning. How are we doing? It's good to see you guys again. And so today we're going to start to look at these waveforms and see if we can know how to read them if we're given a graphical presentation of it. Now I want you to be really careful about one thing. Before you start reading these graphs, you need to look at the x-axis and see what is that representing. If it's representing time, then when you look at the peak to peak between these two things, you'll be looking at not the wavelength, but the period. That's the time it takes for this wave to go from here back down and up here again. That's one whole cycle. It completes one wavelength, but we don't know what the wavelength is because we don't have this in meters. Like over here, this distance is given in meters. We can determine the wavelength in a picture like this. But in a picture like this, all we can do is determine the period, the time it took for one whole wave to get completed. So let's start with this picture up here. The question says, what is the wavelength of the wave above? Now, they don't give us the distance from one peak to another, but I hope you can see that there is start from here, 1.5 waves are making up 8 meters. So one wavelength must be 8 meters divided by 2.5. And so that would give you the wavelength for this particular waveform. Again, I can only do that because this distance is given in meters, and so I can visually see what the length of the wave is. What is the amplitude? Again, remember the amplitude is a distance from the equilibrium point to the maximum point. And so that is our amplitude. This is giving us the distance from one peak all the way down to the next peak. So the middle point, 1.2 meters divided by 2 would be the amplitude for this guy right there. All right, now let's look at this waveform here. This is position versus time. This tells you the height of the wave, and this tells you the distance as it travels. So with something like this, it's easy to find the amplitude, which would be from the middle point here all the way to the top. And it's easy to find the period is the time it takes to go from here to there. So you could just subtract 2 minus 1, which is 1 second. So it takes 1 second for this wave to complete itself. So if the period is 1 second, that's the time it takes to complete one wave. The frequency will also be 1 second or 1 hertz because it's 1 divided by 1, which is just 1. They also ask, what is the amplitude above of this thing? So you could see the amplitude is 6 centimeters. It goes from 0 all the way to 6. You've got to make sure that this center line is going right through the center of the wave, which it is in this case, but it may not always be. So if this wave is moved up or down, you need to find your new equilibrium point. It won't always be at 0. And so the amplitude here would be 6 centimeters. And we can see that there's 1, 2, 3 complete waves. And the period is 1 second, the distance or the time taken from here to there. So you can measure that. You can even go from here to there, 1.5 minus 0.5, again, give you 1 second. And so the period will be 1 second, and the frequency would be 1 hertz, which is just 1 divided by 1, which happens to be the same in this case. Let's look at this one. If I asked you guys, hey, what is the period of this thing? You see you can't find the wavelength because this is given in time. This is in seconds. So what is the period of one wave? And you could say, okay, what's the time it takes to complete one whole wave? And it looks like it's 0.5 seconds to complete one whole wave. So then this period would be 0.5 seconds. Frequency would be 1 over 0.5, which would be 2 seconds. The amplitude, I hope you can see, is 2 centimeters. And that's basically how you work through these questions. It's really, really simple. You could pick from a trough to a trough or a peak to a peak and see what is the distance. It's kind of easier to see it from here because it's right on